Thanks to everybody for logging in. I'm Stuart Haszeldine from the University of Edinburgh. I'm a co-investigator in the UKCCS Research Centre, led by John Gibbons, who we've just been speaking with. And at the University of Edinburgh, I am what we believe to be the world's first professor of carbon capture and storage, which was 3 cycles back in the UK CCS endeavour. We had several power companies involved, electricity companies, one of which was Scottish Power, and we created that chair of carbon capture and storage at the time. And so I'm still based at the University of Edinburgh, and here is a picture of the central part of the University of Edinburgh, and the title of what I'm talking about is Permanent Storage of CO2, and we'll talk about why that permanent is in there in a little while. And University of Edinburgh, with this blue plaque, was the place in the world where carbon dioxide was first isolated in the 1760s. And this Georgian part of the university, in this building on the northwest side of the old university quadrangle, was the chemistry department, and those rooms there were where carbon dioxide was first isolated. And you can still see some of the glassware from that period in the museum just around the corner in the Royal Museum of Scotland. So what I'm talking about here is the antidote to wealth creation, if you like, or the antidote to carbon production, which has been a foundation of a lot of our wealth creation. So in the 1600s and 1700s, the UK was the first country to really have industrial extraction of coal and use that to create industry and feed the products of that coal into the communal atmosphere bath here of air plus carbon dioxide from coal. And then in the middle 1850s, we discovered lots of oil, liquid oil, and managed to produce, and still are producing, lots and lots of oil, feeding that carbon dioxide into the atmosphere. And we've also then discovered that we can produce lots of methane gas, and in some countries, lots of shale gas, and are feeding that carbon dioxide into the atmosphere. So not surprisingly, the atmosphere pre-industrial, as it's called in climate modeling terms, the pre-industrial atmosphere had a much lower carbon dioxide content than it does at the present day, because we've not yet found a way of taking carbon dioxide out of the atmosphere and putting that back underground. So the pot of gold we're looking for in all of this is to intercept these flows of carbon dioxide instead of going into the atmosphere, to put those directly under the ground, and in some cases to take carbon dioxide directly out of the atmosphere and put that underground. So the medium, the common medium, is the atmosphere, and we know from measurement, we don't need any climate modeling, we know from measurement that the carbon dioxide content of the atmosphere up this vertical axis has systematically and relentlessly increased since about the time I was born up until the present day. So the red is the graph showing you the content of carbon dioxide as measured on the top of a volcano in Hawaii. So it's remote from any industrial sources, so that relentlessly increases with a seasonal variation, winter to summer, and irrespective of all the renewables in the world, and irrespective of all the efficiency, and irrespective of everything that's been done, that CO2 content is still relentlessly increasing. And as a consequence of that CO2 increase, then that CO2 in the atmosphere dissolves in the upper ocean. And the amount of CO2 in the upper ocean is shown in the green line. Again, that's a measurement, so we don't need to have any models for that. And the consequence of that CO2 in the upper ocean is that the ocean becomes more acid. So that's the blue line here, and you can see the pH is decreasing, it's becoming more acid. And although that pH is only decreased by about 0.11 units, that's a logarithmic scale. So this means this is about, the upper ocean is about 30% more acid than it was back in the middle 50s. So that's got a serious consequence for plankton and for corals, etc., worldwide. And of course, the CO2 in the atmosphere on this upper right portion here is a greenhouse gas, along with methane and water vapor. And so when the heat from the sun comes in, the CO2 captures that vibration of that CO2, captures that heat on the way out of the atmosphere, so it reduces the radiation back into space of heat. And so the CO2, the water vapor, and the methane stop the re-radiation, the reflection, if you like, of heat back into the atmosphere, into the outer space, and that's what's causing the heating of the world. CO2 is also causing the acidification of ocean, the heating of the ocean, the warming of the ocean is also causing sea level rise just by expansion of the water. And of course, the warming of the atmosphere is causing ice melt off land in the South Pole and in the on ice masses such as Greenland, or glaciers in the Himalayas, and that again is driving sea level rise. And so we're in a fairly difficult position climatically, and this is an unprecedented, as a geologist, this is an unprecedented rise, an unprecedented speed of rise. This has never happened that we can see in any geological history before. CO2 has gone up to this level several times before and has exceeded this level, gone faster, greater than this level, but never so fast. So the rate of climate change is much faster than the rate that animals and plants and life can adapt, and that is going to be a problem. So as humans, we've studied this, and the Intergovernment Panel on Climate Change, composed of several hundred scientists globally volunteering their time, has produced this amongst other graphs. This is a critical key graph. This tells us the temperature increase above pre-industrial through time. So the black line and the black dots are actual recorded historical data. So that's the temperature through time plotted against the total carbon dioxide emission. But actually this is plotted in billions of tons of carbon, which is obviously 3.5 times less than the tonnage of CO2, but it's still a carbon increase. And what this shows you, very important, this shows you is that the more carbon you put into the atmosphere, the accumulation of carbon is pretty much linearly linked in a straight line relationship to the temperature increase. So you can say from this that doubling the amount of CO2 in the atmosphere causes about 2.5 degrees of warming in the atmosphere. And so where we are now, around 2020, we've put about 500 billion tons of carbon into the atmosphere. And if we follow these lines, which are derived from computer models of climate, these are the models, the computer models produced by multiple teams of scientists around the world, then you can see that if we do nothing, then by 2100, we have a 50% probability of 4.5 degrees rise of temperature. So a 50% probability of 4.5 degrees rise, but a 10% probability of being off the graph of an 8 degree rise. Okay. Now 10% probability of 8 degree rise is pretty much extinction. A probability of 4.5 degree rise is again unprecedented in its speed, and we have already seeing the effects of changed weather, and I guess we can see the effects of these heavy rainstorms we're experiencing this week. That's the effect of just 1.2 degrees of temperature rise. So the prospect of going to 4.5 degrees temperature rise with a 50 or even greater is catastrophic. Okay. So total emissions are the problem. So we have to reduce emissions. We have to pull back emissions. We have to not put any more emissions into the atmosphere. The rate of emission is much less important than the total. And we can do that. We know we've got techniques for doing that. We've got carbon capture and storage to reduce the rate of emission. We've got renewable energy to switch energy generation sources from fossil fuel to renewable energies. We've got efficiency to use energy more efficiently and have 3 people in a car instead of 1 person in a car, as for example, or have LED light bulbs. Those are all efficiency mechanisms, and those have been effective. But as we've seen in the previous graph, the CO2 content of the atmosphere is still increasing and increasing and increasing. So this stock of CO2 in the atmosphere is almost entirely derived from fossil carbon dioxide, which is released from coal, oil and gas, but also from industrial processes such as cement making and iron refining to make iron and steel. So the principles of carbon dioxide capture and storage are familiar to you, I hope. So again, just to remind us, the idea is that we can carry on extracting solid fuel, solid carbon from coal mines, for example, or liquid fuel from oil or gas in depleted in oil or gas fields, take that to wherever we're going to use it, a power station or a hydrogen making station if we're going to split methane gas into hydrogen and carbon dioxide, or an oil refinery or a steelworks or a paperworks. We can use that fossil fuel, but instead of dumping the carbon into the atmosphere, then we capture the carbon dioxide, liquefy that as 95% or better purity carbon dioxide, and then inject that for storage, permanent storage, at least 1 kilometre deep underground in saltwater filled aquifers or in depleted oil and gas fields. So in principle, this is really quite straightforward to do, but there's a lot of nervousness amongst governments about actually getting on with this. And the questions which people perennially ask, or perennially for the past 15 years, people keep asking the same sorts of questions, which is, isn't this expensive? And how are we going to finance it? And are we sure that the carbon dioxide will stay there? So I'll talk about the carbon dioxide staying there in this presentation, how we know carbon dioxide works and stays down there. And I'll talk a little bit about financing later on, because I don't think we've got either of these correct yet in the UK. We're on a good pathway to starting, but we're not on a good pathway yet to sustainable, normal carbon capture and storage as a method of reducing emissions. So to put that slightly differently, here's a perspective diagram to try and give you some impression about what happens. Here's a power plant or a factory or something at the surface, extracting its coal, perhaps, burning the coal, capturing the carbon dioxide, and the carbon dioxide, instead of going up the chimneys into the atmosphere, this is a point source of maybe 14% carbon dioxide in the flue gas of a coal fuel power station, or 4 or 8% in the flue gas of a gas fuel power station. We can liquefy that and pipeline that carbon dioxide and inject that down these boreholes, these very, very thin holes in the ground, which are just like telegraph poles, but very, very long. Except they're thinner, they're only about 15 centimeters wide at the bottom, 6 inches wide at the bottom, and we're going down to at least 1 kilometer down and maybe 4 kilometers down, where we can find layers of porous sandstone rock overlain by an impermeable layer of mud rock. So that's what's shown conceptually on this top diagram here. Here we've got a cutaway picture, a slice through the rock, greatly magnified. The yellow are the sand grains, the grey shading is the impermeable rock above, and the carbon dioxide in white, liquid carbon dioxide, pushes the salty water out of the way and is reservoired and stuck there underneath the ground, and can stay there, as I'll try and show you, for at least 10,000 years, and preferably for millions of years. So we're dealing with very, very long timescales. And the size of CO2 storage is conceptually, again, shown by this picture of a piece of North America, where we've got a sandstone which is maybe 100 meters in thickness, very, very thick sandstones. And the size of that sandstone goes as far as you can see. So the size of these area of these sandstones is the size of a small city. So it's the size of Edinburgh or Nottingham or Liverpool or something like that. So in the UK, these thick layers of sandstone and these large areas of sandstone reservoirs, which are good for CO2 storage, always occur offshore. Underneath the UK, the geology is much more complicated and faulted. You can store some CO2 underneath the landmass of the UK if you really wanted to, but they would be small sites and much more difficult to get planning permission. So that's the concept of CO2 storage. And before we enter into the details of storage, I want to talk for a little bit about permanence, because there's a lot of conversation about the moment between nature-based solutions for CO2 storage or geology solutions for CO2 storage. And what that means is that geology solutions, geology remedies are locking up the CO2, let's say as a mineral, so calcium carbonate, CaCO3, there's carbon in this chalk here, was in the sea about 100 million years ago, up to about 60 million years ago, and that then precipitated as a chemical solid to the base of the ocean through the coccolith algae growing in the upper part of the ocean, and that carbon has remained stored in that rock for, as we say, 100 million years since it was deposited. So it's had a very, very long and secure life as CO2 stored carbon. and we know where it is. We know how to calculate the mass of that, and it's not going anywhere. By contrast, there's a lot of enthusiasm at the moment for planting trees or growing hedges or tending farmland in a different sort of way to store carbon in soil or in hedgerows or in trees. And of course, that's a very familiar type of timescale and a very familiar landscape. So that's very easy to communicate to civil servants, public, politicians, etc. But actually, I'll show you in a minute, this is a very short timescale. How long does a tree last? How long does a forest last? How long does a hedge last? So we've got a dialogue between short timescale, easy to understand storage, or very long, secure timescale, slightly more difficult to understand storage. And we know from climate modeling and understanding the way the processes in the earth work, that here, if we want to store CO2, or here we're emitting CO2, sorry, if we emit the tonnage of CO2, more and more CO2 emitted through time along the horizontal axis, if we emit a lot of CO2 very quickly, as we're doing right now, as I mentioned, this has never been done before, initially CO2 then decreases by nature, by dissolving into the seawater, by weathering of rock, carbonate rock, by weathering silicate rocks like basalt and volcanic rock, and then very, very slowly weathering the rock on the seabed, deep seabed. And so that CO2 spike, which we can put into the atmosphere in a few tens of years or 200 or 300 years at the moment, takes more than 10,000 years to decrease back to its previous value. So CO2 residence in the natural system is really very long. And so we can store that by geological means, by capturing CO2 and putting that back underground. So we can have one intervention and we can capture maybe 10 million tons a year from one project or 5 projects, and we can store that. And once we've injected that, that CO2 stays underground for geologically long time periods, for tens of thousands of years. Alternatively, we can grow some trees and capture some CO2 in trees, but the lifetime of a tree, a commercial tree in the UK, is maybe 40 years. The lifetime of a hardwood tree in the UK is maybe 100, 150 years. So trees are very, very short lifetimes. They will increase the capture of CO2 and stock that CO2 into a tree, but it won't store it. So the tree, once the tree dies, it rots away. Once the roots die underground, they rot away. The carbon in the soil goes back into the atmosphere. So if you want to store carbon in living trees or wood, then you have to repeat that tree growing cycle at least 100 times in future generations, every 40 or 50 years, for 100 times into the future to get the equivalent value out of the storage. So what I've contrasted here is the slow geological cycle in the chalk with the fast biological cycle in the trees and the hedges. So we've got our carbon in the atmosphere, we can capture that, or we can inject that into the ground with carbon capture and storage, or we can rely on vegetation to capture that for us and put that into the biosphere. And of course, right now, the capture of biological CO2 is very cheap, £10 a tonne. The capture of geological CO2 and storage of geological CO2 is much more expensive. So it would appear obvious that we shouldn't bother with carbon capture and storage, except, of course, when you consider the permanence. So the permanence, how long that stays stored for. I showed you the chalk, that's stayed stored for millions of years, tens of millions of years. We need at least 10,000 years, so that is going to stay stored once we've stored it. By contrast, the biosphere CO2 will not stay stored. You need to renew that every 100 years, so that the total cost to store for 10,000 years is still about just £120 a tonne for geological carbon capture and storage, whereas it's well over £1,000 a tonne for biological storage. And of course, you've got no guarantee of call that this biological storage will be renewed and renewed by future generations. Okay, so the value of geological storage is in its permanence, it's easy to understand, monitor, its monitorability, and its huge size, which we can access very easily. So I'm going to talk about some of those attributes of geological storage. And as we probably know, this is already operating. We can put immense tonnages underground. It's exceptionally secure. It's the most secure way of storing carbon which we know of. And we can do very accurate and precise monitoring. But our problems are the pace of CO2 storage is way too slow globally and in the UK, and we have to make it profitable rather than subsidizing it. So I said CO2 storage has been happening already for years and years. Since the 1970s in the United States, carbon dioxide has been transported by pipe, injected into the ground and flushed through rock to dry clean the oily rock and to dry clean the oil out of the rock and bring extra oil to the surface. But that still is CO2 transport, capture, transport and injection. And all of that CO2 can stay underground if you want it to. So this is by far actually the most secure way of storing carbon dioxide, because by pushing it through the rock, you force it to dissolve in the water. So that's known, secure, been operating since the 1970s. But of course, the CO2 storage you inject tends to be offset by the extra carbon you produce. We can go into that in questions if you want, but it's quite possible to design these, a government to design this to store net CO2 if it wants to. It's just that the United States hasn't bothered to do that. By contrast, here we have the storage site in Sleipner in the North Sea, central part of the North Sea, midway between the UK and Norway, where the Norwegian company Statoil, now Equinor, has been producing hydrocarbons from the Sleipner East field. Those have natural carbon dioxide in them that's brought up to the platform in the sea here and stripped out in the Sleipner T platform. And that carbon dioxide is re-injected into the nearest available saltwater aquifer, this saltwater-filled body of sandstone rock called the Utsira Formation, which is at 1 kilometer depth. And that has been done for the explicit purpose of protecting the climate by the Norwegians since 1996. And they enacted that by the very simple method of charging a $50 a ton tax on any carbon dioxide emissions offshore. So Statoil took about half an hour to work out that they could capture and store the CO2 for a much cheaper price than that $50 a ton. And that's what they've been doing since 1996. And of course, have developed the Snøhvit capture and storage operation at the north end of Norway subsequent to that. And that experience since 1996 now means that the Norwegians are several years ahead of the UK in creating a CO2 injection and storage market. Okay. And it's the market again for the price for CO2, which is important, because in the US there is no market for storing CO2, it gets sold for enhanced oil recovery. Because in Europe, there's a tax placed on CO2, or there can be a value placed on CO2 if we play it right, then there can be a commercial means to store CO2 for climate purposes. So the technology is not a problem, but the market is a problem. Okay, so this uses oil and gas technology, offshore oil and gas technology, which we're very expert at in the UK. We've got globally leading expertise. We understand our offshore geology extremely well. And here's another visualization of that Sleipner project, injecting CO2 into that sand reservoir, which again is about 100 meters in thickness, 1 kilometer below ground. And by using seismic reflection oil field techniques, we can inject that CO2, and then using the seismic, we can monitor and watch the layers of CO2 as they grow and spread underground. And that's not just restricted to the UK. Here's an example in Alberta, Canada, where Shell have developed the Quest storage site. Here's an oil refinery in the north of Alberta. You can see that Alberta's got very simple geology because it's very, very flat. The rock layers are very, very simple underground. Shell capture about 1/3 of the carbon dioxide from a hydrogen upgrader as an industrial process inside that refinery and send that carbon dioxide to storage. And that's been operating again at 1 million tons a year since late 2015. And that is here in the central part of Alberta, capture and storage, and that's could be linked. There's current enthusiasm in Alberta for getting much more carbon capture and storage done by building a trunk pipeline to link the sites of CO2 arising to the sites in the north to the sites of CO2 storage in the south. That's busy happening. And of course, the layer cake geology is very important. Here's the borehole going down to these very, very simple layers of rock, but it's exactly the same thing, a porous sandstone overlain by an impermeable mud rock to keep the CO2 physically contained. And because we know what we're looking for geologically, then around the world we can go and make an atlases or surveys of where the CO2 storage sites are and what the capacity is. So here's the United States. In brown, we're showing the sedimentary basins, the thick accumulations of sediment where the sediment layers may be 3 or 5 or 8 kilometers in thickness. And in blue, some of the easier and most accessible candidate regions for CO2 storage, just simply shown as rectangles with the storage capacity in billions of tons of CO2 storage. And you can see that different sedimentary basins all around the United States have very large amounts of potential for CO2 storage. And since this was made in 2012, the Gulf Coast of Texas has now leaped up the pathway, and Americans have realized they can store CO2 in the oil field sandstones underneath this Gulf Coast of Texas, and that'll probably be one of the main places that CO2 gets stored. So in a place like the United States, here's 150 or 160 billion tons of CO2 storage, much, much more than is needed for at least 100 years into the future. And developing this is in principle well understood. People have been injecting CO2 for decades, and the rate of development is just limited by how much you can put down through a borehole at any one time. And that's usually about 1 million tons per year per borehole. But in a suitable sandstone where you can let the pressure diffuse, I'll talk about pressure again later, where you can let the pressure diffuse, you could put up to 4 million tons a year down one borehole. We've done the same sort of thing in the UK. Here's an example which we did in late 2000s, and then has been followed up by the UK government and what was the Energy Technologies Institute, surveying the sandstones offshore. Each one of these blobs, orange blobs, is a sandstone reservoir which you can fill up with carbon dioxide, and the oil and gas fields are shown in dark red, and gas fields and condensates in yellow, and the main gas fields are further south. Of course, in the southern North Sea, same thing works. And the point is, for the UK, we've got lots of industrial sites, particularly along the east coast, which have got really close access, good access to huge amounts of CO2 storage. And so if we look forward to like a 2050 setting, then we could have huge amounts of pipework and an industry comparable in size to the present day oil industry offshore, because we've got about a third of the storage for Europe. And at the moment, we're very obsessed with developing these clusters in Scotland, or in Teesside, or in Humberside, or in Merseyside. We're quite obsessed with developing those clusters, but those are just a start of what we could be thinking of as a much larger scale network of storage beneath the North Sea, where we've built storage pipes and developed storage sites specifically for the injection and storage of CO2, not just for the UK, and not just for shipping from Cardiff or from southeast England to storage sites in the North Sea, but we could also bring in carbon dioxide from Europe, because, as I said, we've got a third of the CO2 storage for Europe. Norway have got another third. We could be developing a business here which is worth billions of pounds per year just in straightforward revenue, let alone the extra employment which that can create. So at the moment, we're busy just developing the very first industrial clusters, but we should start having an eye on how we're going to develop this as a European scale green business. Otherwise, the Norwegians will take all the business and we won't have any. So let's look a little bit about injection flow and monitoring, the details of CO2 storage. So here's what CO2 storage is: injecting CO2 into a sandstone here. And CO2 is buoyant. It sits between the sand grains in this magnified picture here. CO2 is between the sand grains. CO2 is buoyant and moves between the sand grains and flows sideways underneath this layer of cap rock, this impermeable cap rock. And as it moves, the CO2 dissolves in the water. And so by moving, the CO2 leaves little bits of carbon dioxide behind it as residual saturation, That's a good trapping mechanism. It dissolves in the water. So by dissolving, it's also a trapping mechanism, because once it's dissolved, it stays there forever. And the third mechanism, of course, the physical mechanism of trapping underneath that cap rock. So it's absolutely secure. We can go around the world and understand that a lot better by looking at natural examples of CO2 storage. So I'll just show you three. So here's the Miller oil field and the Bray oil field in the central part of the North Sea. This was one of the first bits of work that we did to understand the security of CO2 storage. So here in cross section from west to east here, across the edge of the faulted graben, here's the sandstone of the hydrocarbon field with the dots overlain by the mud rock seal. And we can look at the chemistry, the geochemistry of the minerals in that mud rock and understand that CO2 dissolved in this oil and forming a gas cap on top of the oil field, that carbon dioxide has very slowly diffused through that cap rock and has got as far as 5 meters in 60 million years. So for the timescale which we want to do, 10,000 years to isolate CO2 from the atmosphere, the carbon dioxide is going to diffuse about 2 centimeters. Okay, so this is an example of how great the storage security is of geological storage. In what if it leaks? People always ask that type of question. And if we want to know what happens when CO2 leaks, then it's a great idea to go and find places where CO2 leaks. So here's Italy. This is the leakiest carbon dioxide country in the world. And here is the central part of Italy. Inset on that map shows where Italy is, in case you don't know. Sicily's down the bottom, Rome is about here. And because there are lots of volcanoes in Italy, and because it's there's lots of rocks becoming deeply buried, there are lots and lots of natural CO2 emissions from that volcanic CO2, for example. So these hollow and these filled dots are the sites, over 300 sites of CO2 natural emissions in Italy. And people have lived with those for thousands of years. So here is the largest CO2 seep in Italy at Mafite. And this is a seep, a natural seep, equivalent to the emissions of a gas-fueled power station every year. So if you plumbed a gas-fueled power station and didn't capture the CO2 and just emitted that out onto the landscape, this is the immediate damage around that site. So it's very small amount of damage because the CO2, the dense CO2 rolls down this gully and mixes very quickly with the atmosphere. After about 200 meters, the CO2 is just mixed into the atmosphere. But this has been known as a site since pre-Roman times. So this is an archaeological site of pre-Roman offerings to the underworld. And so again, people have learned to not go into that site. Here it says pericoloso morte or something like that. So that's Italian for keep out. But you can see they've not even bothered putting a fence around it. Here are other seeps in Italy. So this is Jen Roberts researching that. You know, somebody has to go and walk around Italy to have a look. But a normal CO2 seep bubbling away up a fault zone just bubbles away quietly here with a cold seep of bubbling CO2 in with water. And so the impact of CO2 leakage is absolutely trivial locally. The problem, of course, of leakage is what, you know, if you're trying to store CO2, how much comes back. But actually we've calculated that, and these seeps, they're called seeps rather than gushers, so they seep out very, very slowly. So even although these are sites which have not been looked after underground and are leaking naturally, the risk of death is tiny. So the risk of death from any one of these seeps is one death per year in 30 million of the population. So it's actually much, much less death rate than the regulation for radioactive waste storage. So this CO2 storage, even though it's leaking, is really still quite secure. And we can calculate that these seeps have been leaking slowly for tens of millions of years in some cases, and have still retained more than half of their carbon dioxide. So even though it leaks, it's still a lot better to have put it there. So in the worst possible case, CO2 storage is still better than dumping it into the atmosphere. The third example is here in Canada. There's a site at a coal gasification plant in North Dakota, which produces methane from coal and other chemicals from coal. and that pipeline captures its CO2 and pipelines its CO2 into Canada for enhanced oil recovery at Weyburn Field. And this is where on the flatlands of Canada, here again in the Alberta basin, here's a 1 mile scale bar. CO2 is injected up here, and the people on this farm down here decided that their dead cow was caused by CO2 leakage from 7 or 8 miles away. And so they got people in to analyze the CO2, and there was a claim that the CO2 was leaking. But we and the University of Texas went there and used fingerprinting of CO2 ownership, chemical fingerprinting, using isotopes of carbon and isotopes of noble gases. And we can tell that the CO2 we measure, the helium traces in the CO2, part of the CO2 dissolved in the CO2 we measure at the surface, are undoubtedly due to mixing of that injected CO2 with air, and mixing of any produced CO2 from the shallow subsurface is mixed with air. So this is just natural CO2, and the same is shown by carbon isotopes. That falls on the trend of natural CO2 in the soil mixing with air. So again, you can use natural sites and engineered sites to help you understand how to understand CO2 retention and how to identify CO2 if it does leak. But I'll just mention again the storage of CO2 in the tiny pore spaces between these sand grains here. Okay, that's where the CO2 sits. And remember, the CO2 is trapped as the white CO2 between the sand grains, trapped physically by the seal on the top, trapped as isolated bubbles, as capillary trapped CO2, which cannot migrate anymore. The third method is CO2 dissolved in the water to make dense, fizzy, salty CO2 underground. And the final method is very slowly to form new minerals. So this trapping of CO2 underneath the seal is instant. The dissolution of CO2, the trapping of CO2 as isolated bubbles happens whenever the CO2 moves. And the dissolution of CO2 takes just a few tens of years. So it's actually really difficult to get CO2 out of the ground. Once it's trapped, it's trapped. We can understand that, we can visualize that by using computerized scans, by taking samples of rock from the underground, scanning by CT scan, just like hospital imaging, looking at three-dimensional images of those sand grains and where the CO2 is accumulated in the rock. So here are these cores of rock imaged at Imperial College by Sam Craver's work. And that helps us to understand the CO2 distribution at micro scale. And then we can then scale that up to a meter scale and a tens of meters scale. And we can then scale that up to a storage site scale at a kilometer or 2 or 3 kilometers scale. So we have a really great understanding from the sand grain to the kilometer scale. And that kilometer scale is just one of these structures of storage here on the left-hand side, of storage within a sedimentary basin east of Yorkshire here. Here's Filey Brig in East Yorkshire. So there are several storage sites offshore. So we can understand everything about that CO2 right from the sand grain scale to the tens of kilometer scale and the regional scale of tens of kilometers. And of course, there are lots of ways that CO2 could leak. And here's a compendium of a theoretical set of leakage. And this is theoretical. This doesn't mean it actually happens. So this has been well examined since the early 2000s. CO2 can be injected down a borehole. It could leak up the borehole. That's the main story. That's the main method of leakage, the most serious method of leakage. It could leak sideways out of the field. It could leak up a fault. It could leak through different layers of rock and eventually get out of at the surface. But all of this is numerically and statistically extremely unlikely. And again, that's what we've got. One of the things we've got by going to natural analogues, by trying to understand these processes of CO2 migration and leakage, show that it's incredibly unlikely to happen. And by far the greatest leakage potential is to leak up the site of the borehole injection. And of course, that's very easy to monitor, because if that happens whilst you're injecting, then you know that you need to fix that by injecting, by recompleting the borehole, by putting extra cement down the borehole. So these are easy to monitor effects and easy to fix effects. And at the CO2 in the Otsira formation, this monitoring is really well displayed by using seismic reflection, by bouncing sound waves down into that layer of CO2, and those layers of reflection show you the layers of CO2 before injection, after some injection 3 years later, and after some more injection 3 years after that. So you can track precisely where the CO2 is. And this storage site, which has had an exceptional amount of seismic surveying, shows you that you can detect 100 tons of CO2 at the top of that layer. So if that's trying to leak out, you could detect just 100 tons of CO2 leaking and get several years, if not decades, of warning before any of that CO2 comes to the surface. So again, this is very secure, very easy to monitor, well understood monitoring. And to put that in terms of nature-based solutions, this is better quality monitoring than you can do for nature-based solutions. So this is equivalent to looking at 50 trees in a 10 million tree forest. And I don't think any of the nature-based solutions would guarantee that level of storage security. I mentioned boreholes. Again, that's been very well researched. So here's a borehole casing going down into the ground with cement between the casing and the surrounding rock. Obviously, the cement can react with the CO2. Ordinary Portland cement does react slowly with CO2, and we know how fast that happens because we've gone to the places in the United States which have been drilled for carbon dioxide back in the 1970s, extracted samples of cement and rock and casing and looked at that reaction rate, and the reaction rate is incredibly slow. There is a detectable reaction rate, but it's slow enough to be well, absolutely not a problem. And we can also, there are now constructed CO2 resistant cements. If you want to deliberately renovate a well or block off a well, then you use these commercial cements. So I'm running slightly late, so I'm just going to skip through a couple of slides. Pressure is very important underground because for monitoring and closure and post-closure certification of security. So here's an example of that. This is a theoretical model, a computer model of the Illinois basin, an entire sedimentary basin. So these are kilometers. So that's 100 kilometers, 100 kilometers, 100 kilometers. So this is a huge area. And what this says is if we've got some boreholes and we inject CO2 into the center of the basin, the physical CO2 stays in the center of the basin, but the effects of the pressure ripple out and are very rapidly detected throughout the basin. So after 10 years, the CO2 is contained within 1 or 2 kilometers, but the pressure effects have gone 200, 300 kilometers. After 50 years, the pressure reaches several hundred kilometers to the edge of the basin. But then once you've stopped injecting in these boreholes in the center, once you've stopped injecting, that pressure diffuses sideways and downwards in the sedimentary basin. So the pressure decreases again. And after 100 or 200 years, you're effectively back to what you were before you injected CO2. So the pressure is a transient effect, but it's very important to manage the pressure, because if you inject too much CO2 too fast, then you'll fracture and break the rock. So that's fracking, and you don't want to do that. CO2 storage is the opposite of fracking. But again, we know exactly what to do. We know the strength of the rock. We can measure the rate of injection. We can measure the pressure underground, so you can have a very good safety margin and manage the boreholes to do that. So here's an example of how that might work in the North Sea. Here's a bit of the Captain sandstone offshore of Scotland. Here's a typical bit of the Captain sandstone in yellow outline here with the seismic reflection information off the top of that sandstone. And there are several oil fields in there already. These clusters of boreholes show you where there's clusters of oil fields. And the question is, if we've got the possibility of 2 sites to inject 20, 40 kilometers apart, will the pressure interfere? Will that damage the injection? And of course, the answer is yes, the pressure will interfere, but we can simulate how that pressure interferes by using a computer model, just like the reservoir models which oil and gas people use all the time. Again, this is known technology. If we inject CO2 here in site A and CO2 in site B, we can see the pressure rippling out, just like I showed you in that sedimentary basin, up this thin sandstone, and the pressure will eventually connect after a few 20 or 30 years of injection. but we can quantify that, we can measure that, we can predict that. And most importantly, we can use the pressure measurement as a method of surveying the effectiveness of that CO2 injection. So by measuring pressure rather than is a very cheap, sensitive, low cost, continuous way of measuring CO2 injection success. And that's much more likely to be used by oil and gas companies storing CO2. They're not going to do seismic surveying every 2 years because that's too expensive. They are going to install pressure meters and survey the pressure and maybe survey seismic every 10 or 20 or 30 years. Okay, so here's a typical example of a conformance monitoring of checking how well your CO2 site is performing. So by measuring the pressure away from a storage site, or by measuring the microscopic, undetectable, unfelt earthquakes. Lots of earthquakes will happen, but they're undetectable by people. They're entirely natural, natural effects of injecting some CO2. But you can see that the monitoring is done by downhole monitoring deep underground, by looking down into the ground through seismic and by radar interferometry at the surface, by satellite monitoring, by measuring what's going on in the deep groundwater, by measuring what's going on at the seabed or the land surface, by measuring what's going on in the atmosphere. And that lasts for maybe 20 or 50 years into the future. And a problem for many oil companies is that when they're disposing of CO2, the government, the regulatory authority will say, okay, here you've injected from over a 5-year or a 10-year period, and we want you to carry on monitoring for decades and decades into the future. And actually that's entirely unnecessary. Once you've understood the field well enough and had successful injection, if that has behaved as predicted for a 5 or 10-year period, that's actually enough. And so it's very easy for a government to over-regulate this amount of storage and ask for very large amounts of financial security, which are entirely not necessary. Because just to go to the right-hand side of this, we did some work about quantifying how much CO2 can leak and how much CO2 will remain stored. So here's a cartoon of a fold underground, CO2 stored in that structure, how fast and how much CO2 could leak from this archetypal structure. So we compiled all the information we could find about CO2 leakage from natural analogues, CO2 leakage from boreholes, CO2 leakage where things had gone wrong. And our conclusion from that is that if in a well-regulated site where there's monitoring, then 98% of the CO2 which is injected will stay there for 10,000 years with a 50% probability. Okay, so that means that 2% of the CO2 might leak out. Okay, so asking storage operators to ensure for 100% of the CO2 in case that leaks out is entirely overkill in terms of regulation and over-regulation. And so again, what you need to do is be very tight on the regulation whilst that CO2 is being injected and in the immediate 5 years or so afterwards. But once it's down there, it's going to stay there. It's really hard to get the CO2 out. Flow assurance, I'll skip some time, not talk about that. The main problems with CO2 storage, last couple of slides I'll talk about, is if we look at the historic amount of CO2 storage, then we've done a little bit of CO2 storage, which is all grant funded worldwide. United States, Australia, UK, China have all grant funded CO2 storage. The rate of CO2 storage you need is literally orders of magnitude greater than that. So we're running in the UK at about 5 times too slow for our 2030 objective. We should be aiming for a 30 to 50 million tons a year objective if we want to hit net zero in the UK. Worldwide, we're running at about 100 times too slow if the world wants to meet net zero in 2050. So that doesn't mean CO2 storage is bad. It means it's underfunded and nobody's paying for CO2 storage. It means we will be able to do CO2 storage, but we'll not get to our required amount by 2050. We'll get there in 2150. So we'll overshoot on our heating objective for the global heating. And it's worthwhile saying that these models work, these objectives work from International Energy Agency projections, which have either assumed a carbon price of £5,000 per tonne of tax or penalty of CO2 release, or have just assumed that CO2 storage will happen without, and the net zero modelling just assumes CO2 storage will happen without any price being too high. So it's probably even more than that. In Europe, we need to scale up our storage, this complex graph here, but we'll just look at the white circles. In Europe, we're storing about 1 million tonnes a year at the moment in 2000 and 2010. Going forward to 2050, we need to scale that up to 10 million tonnes a year, 100 million tonnes a year, 800 million tonnes a year. So what that means is in Europe, we need to be putting CO2 into 50 boreholes a year from 2025. We're nowhere near that objective. So the rate of storage development is much too slow. If we look at this in terms of a climate graph, CO2 emissions per year, time into the future, historical CO2 storage in black, the country pledges for the Paris meeting of the Intergovernment Panel on Climate Change and the conference, which will be in Glasgow this year. These are nowhere near what you need to be on for sustainability. So one objective for Glasgow this year is those plans for the future need to include carbon capture and storage and direct air capture, and not just plans, but actual enactment to get way down on this 2 degrees warming sustainability graph. So we're nowhere near a fast enough development of efficiency or renewables. We're nowhere near a fast enough development, particularly of CCS and CO2 storage. And we've hardly started on CO2 removal and air capture, which we need to have at the right-hand part of this graph. So the remedy for this, if you went to Miles Allen's talk, is we think that just asking for subsidies is not nearly enough. What we need to do is place a mandate on the oil and gas importers and producers that they import the carbon, we use the carbon for our products, industry captures the carbon, and then there's a mandate on the oil company to ensure that that CO2 is stored, and the government then checks that that CO2 has been stored. So the change from the present situation is, instead of paying oil companies to do it, we tell them to do it. They charge more for the oil and gas to enable them to do it, and we certificate that once they've done that. So the certification is a mandate of CO2 and a certificate of successful storage. And of course, oil or gas will charge more for that, but it's a small extra percentage, and it's much cheaper than any other method. So here is a graph of carbon price through time. The blue lines are enactments of the IPCC pathways and the international energy pathways, where the carbon price goes up to thousands and tens of thousands of pounds a tonne to try and force people to store CO2. Alternatively, if you just tell people to store CO2, the actual price of doing that is around about $100 per tonne, maybe $200 per tonne, but that price limit will be capped by the price limit of direct air capture worldwide. So a mandate on CO2 storage linked with development of direct air capture is the cheapest, most effective, and most efficient way of guaranteeing some storage. So what I've said, CO2 storage operates routinely. It can be extremely effective. We have all the techniques and technologies necessary. They can be improved, but we've got everything we need to start. And the costs can and will stay low by competition between storage operators. And the demand is comparable in size to the present oil industry. And that is the survival route for the oil industry, if the oil industry wants to take that route, and if governments make it possible for the oil industry to take that route. And the way is not a market, but a mandate. So that's all I've got to say. Thank you very much.